Can you guys online hear me now?
Yes.
All right, thanks. Okay, so I think so briefly you guys can go to the first page. If you are online, you didn't hear me, you can go to the first page of the slides to see the reminder items. And for the lecture part, I think the new content we just mentioned is this Doppler effect. So let me just quickly go through here again. So if you have a source that's moving, the observer is stationary, depends on if the source is moving towards the observer or the source is moving away, okay? So then the frequency heard by the observer will be changed. So this is the equation you can use to calculate. So take this part, F sub O, that's the frequency heard by the observer, and then equals to 1 divided by 1 plus or minus US. U is the speed of the source, V is the speed of the sound, okay? Times the frequency times the frequency given out by the source, okay? You take the plus here when the source is moving away from the observer. It's take negative when the source is moving towards the observer, okay? All right, then we'll be looking at this example here. So basically we are given that, or the equation you want to use is F observer equals to 1 divided by 1 plus or minus US over V times Fs. So it tells you that Fs is 35.0 kilohertz. And it tells you the speed of the source is moving is 3.25 meters per second, okay? And the speed of the wave, of the sound wave in air, uses 340 meters per second, okay? So then calculate this guy, okay? So you need to determine if you need to use the plus or minus, okay, in the denominator. All right, so I think we can take a look on this one together now. So because the bat is approaching the moth, so that means the source is moving towards the observer. So you'll take negative sign here. Okay, so you'll take f of O equals to 1 minus US over V times Fs. Okay, so this would be 1 divided by 1 minus of 3.25 meters per second over 340 meters per second, and then times 35.0 kilohertz. Okay, and this will give you 35.3 kilohertz. Okay, so you can see your frequency increases, right? Part B is asking you if the speed of the bat increased, the frequency heard by the mouse is higher or lower. Okay, so if you have this increased, okay, then this whole thing will increase here. So 1 minus of that will be decrease. Okay, so the denominator will decrease. Okay, then 1 over of the denominator will increase. Okay, so this thing will increase. Okay, so that's how you can tell it's going to be increase or higher frequency heard by the moth. Okay. All right. We can calculate it again, given the speed is increased to 4.25. So that's the same equation. You are plugging your numbers. So 1 divided by 1 minus 4.25 over 340, and then multiply by 35.0 kilohertz. That will give you 35.4 kilohertz. Okay. So it's increased a little bit. Okay. Any questions you guys might have on this one here? All right. So in this case, your source is approaching the receiver. So you use F equal to 1 minus US over V times Fs. Okay. So this is when source is moving towards the receiver or the observer. Okay. You'll take, if you use this equation, 1 plus US over V times Fs when the source is moving away from the observer. Okay, so all right. All right, there's a question asking, is it possible that for the denominator to be negative? Okay, so yes, it's possible because depends on your U, right? Your US. If your speed of source is larger than the speed of sound, okay, then that will happen, okay? But I don't think we'll see that problem often in this class, okay? That's a really high speed. So usually in our daily life, we don't often see an object moving at a speed over speed of sound, which means supersonic, okay? But yeah, occasionally we will see that, okay? So there's yeah, that's a good question there. All right. And I will show you guys a video about when that happens, then what you expect, okay? All right, now I think in one of the homework problems coming up, you will be asked what would be the frequency heard back. So the sound will hit the mouse, and then it will reflect back to be heard by the bat. Okay, so in that case, you'll have to apply the Doppler's equation, this equation twice. Okay, so the first will be this source is moving, this is stationary, and then so that's what will be the frequency heard by the mouse. We can calculate this. Okay, now when it reflects back, then you will treat that the mouse as the source, the bat as the receiver. So in that case, the source is stationary, the receiver is actually moving. Okay, so we are going to use a slightly different equation on that scenario. Okay, so you're going to apply the equation you learned here, and then the equation you just coming up in the next slides. Okay. All right. So let's take a look on that scenario when the receiver is moving. Okay. So say if you have a source giving out a sound wave, and now the observer is moving either towards it or away from it. So you can actually see that if the observer is moving towards it, then here the pitch change will become higher, right? Because it's approaching it. So then for the next wave to hit the observer, it will travel less distance because the observer is moved towards it. Okay, so frequency will be higher heard by the observer. And then if he's moving away, then the frequency will be lower as he hears that frequency. Okay. So in that case, the equation is slightly different. You are going to use this equation. Frequency heard by observer is equal to 1 plus or minus mu 0. This is the speed of observer divided by the speed of sound, and then times f times fs, which is the frequency given by the source. Okay. And to determine what sign you need to use for the plus or minus. So if the observer is moving towards the source, you take the plus. Okay. And on the other hand, if the observer is moving away from the source, you take the minus sign. Okay. So that's how you determine that. So let's take a look on an example here where the observer is moving, the source is stationary. All right, so this one says when the bell in a clock tower rings with a sound of 475 hertz, so that's your Fs. A pigeon roosting in the belfry flies directly away from the bell. If the pigeon hears a frequency of 448 hertz, what's the speed of the pigeon? Again, use the speed of sound in air as 340 meters per second. So in this case, we are given that the frequency by the source is equal to 475 hertz. And the frequency heard by the observer, by the pigeon, is 448 hertz. Okay. So speed of sound v is again 340 meters per second. It's asking you what would be the speed of the observer that is moving away. So the equation to use is FO equal to 1 plus or minus U sub O over V times Fs. Okay. All right. So let's take a look here together. So the pigeon is moving away from the source. So you can see that the frequency it heard is being decreased. So you're going to take the minus sign here. Okay, so I'm going to take the minus here for that. F0 equal to 1 minus U0 over V times Fs. Okay. Looking for U0, the rest you have them given 448, 1 minus U0 over 343, that's in meters per second, times 475 hertz, okay? So you are solving for your U0, you divide both sides by 475, okay, get rid of that. And then you'll do, so 448 over 475 equals to 1 minus U0 over 343. All right. So what you want to do is you can move this guy to the other side, becomes minus 448 over 475 minus 1 equals to minus of U0, 343. You multiply both sides by 343 or negative of it, get rid of that. So negative 340, actually it's just 340, sorry. I think we're using 340 in this case, okay. So it turns out your U0 will be 19.3 meters per second, right? And you see, looks like there's a chat there. Yes, the 340, that's the velocity, the speed of the sound in air, right? Instead of 343, okay? All right. All right. Now, in many cases, both the observer and the receivers are moving. Okay, so then you combine the two results we got from when just the receiver is moving or just the source is moving. So when you combine the two, the equation actually becomes this guy. Okay, so it becomes V plus or minus U sub O, that means the speed of the observer, and then divided by V plus or minus U sub S, that's the speed of the source, okay? And again, you have to determine if you are going to take a plus or minus sign for the numerator and denominator as well, okay? So this is referring to the source. If the source on the numerator is the observer, so if the observer is moving towards the source, then you take plus. Okay, if it's moving away, you take minus. Now it's the other way around here. If the source is moving towards the observer, you take minus. And then if the source is moving away from the observer, you take plus. Okay. So, and then this is typical the combined equation that you can use this one for the both scenarios. Okay, so in the case if observer is stationary, then simply this one becomes 0. Okay, then you just have to worry about the speed of the source is moving if it's towards or away. On the other hand, if the source is stationary, then this is 0. You don't have to worry about the plus or minus here, but you just have to wonder about how to pick plus or negative on the top here for the observer. Okay. All right. So like radars, they are using Doppler's effect. Okay, so like speed radar. If you ever been stopped by a police car saying you are speeding, then they use radar for that. Okay. And medical diagnosis also use Doppler's effect. Also, astronomical measurements use Doppler's effect. So that applies to not just sound wave, but the electromagnetic waves. Okay, so we can see like how far or how fast a particular star is moving away or towards us by using Doppler's effect. Okay, we can see the color change of that light. Okay, so you can refer to as either a red shift or blue shift in that case. All right. Now, so this is what happens. So when the speed of the source is moving, we can see from, I think from this equation over here. Okay, so if the source is towards the receiver, then you take minus sign, right? Now, if the speed of the source is very large, approaching the speed of sound, so then the denominator will be 0, okay, or even larger than the speed of sound. So this is then what happens. So when that happens, you create sonic boom. Okay, so I'm going to play a video here for this. But the plot here says, so if the observer is moving, so then it's not going to create that problem because even the speed of observer is larger than the speed of sound, you don't get 0 in the denominator. Okay, only when the speed of the source is moving towards the receiver, you'll get that effect. All right, I'm going to play this.
Hey, 42 here. Ever since humans invented the wheel, we have been obsessed with speed. For thousands of years, we have been designing and engineering vehicles and techniques to help us move faster. We eventually invented the car, which allows us to travel anywhere at speeds of up to a few hundred kilometers per hour. We then quickly realized that this was a grave mistake, because all it did was allow us to get to work faster. So we invented even faster aeroplanes, so we can instead go sit on a sunny beach somewhere sipping a pina colada. But this incessant pursuit of speed has come with some strange side effects, namely the sonic boom. At sea level, sound travels at 340.29 meters per second, which is pretty darn fast. But in 1947, some bloke called Chuck Yeager, who was an American test pilot and speed-obsessed lunatic, managed to travel faster than that at 428 meters per second and break the sound barrier for the very first time using a Bell X-1 aircraft. Witnesses heard an extremely loud boom and saw something quite strange, a cone-like object emanating from the aircraft. This will come to be known as the sonic boom. But what is a sonic boom and what causes it? Let's find out. Sound travels as a wave, with crests and troughs. If you were to visualize sound waves, they would look like spheres emanating from the source of the sound, with each ring representing a crest of the sound wave. The crests of the sound wave appear almost perfectly symmetrical when the object emitting the sound is stationary. However, when it starts to move, something peculiar happens. The spherical sound wave crests that are travelling in the same direction as the object get squashed together, and each wave reaches the observer quicker than the previous wave. Yeah, I know that can be a bit tricky to wrap your head around, but basically, when an object moves, sound gets squashed. The result of this sound wave compression is an increase in the frequency of the sound. This means the sound becomes higher pitched as the object comes closer to you. This is why cars approaching you sound higher pitched than when they're driving away from you. Think of it like putting a big burly bloke on a fast roller coaster. His voice may sound deep and full of confidence when he straps himself into that seat, but start that baby up and he starts squealing like a little kid. Okay, that's not totally caused by sound wave compression, more a general dislike for roller coasters, but you get the point. On the flip side, however, wave crests that are being emitted in the opposite direction to which the object is travelling take longer to reach your ears, so you hear the noise at a lower pitch. This is known as the Doppler effect. But why on earth am I telling you about all of this? How does it relate to a sonic boom? Well, it's extremely important to understand the Doppler effect, because a sonic boom is created by exploiting the Doppler effect. Take a high-speed aircraft, for example. As it travels through the air, it is constantly emitting sound waves. Just like any other sound-emitting object, these waves radiate from the source in a spherical fashion. The sound coming from a jet is mostly a mix of engine noise and air resistance as it pushes air molecules out of the way at very high speeds. The latter is what is responsible for that whooshing sound you hear as an aircraft passes overhead. The sound waves being emitted in front of the aircraft are being compressed. The faster the aircraft is travelling, the closer together these waves get. But as long as the vehicle's velocity is not higher than 340.29 meters per second, that's the speed of sound, the waves will never touch each other or overlap, because each wave is travelling fast enough so it can get out of the way before the next wave is emitted. But what happens when you travel faster than the speed of sound, and don't allow each wave enough time to propagate outwards before the next wave is emitted? This is where things start to get funky. When the aircraft exceeds the speed of sound, each sound wave is released ahead of the previous wave, because the object that is emitting the waves is travelling faster than the waves themselves. This causes the waves to get pushed together and create a single sound wave with an enormous amount of energy called a shock wave. If we could see this effect in real life, the sound waves would appear as a cone trailing behind the aircraft. This is known as a Mach cone. In the field of aeronautics, the speed at which sound travels is known as Mach 1. The result of this extreme compression of sound waves is a very deep, audible boom, which we refer to as a sonic boom. Any observer watching the aircraft pass by wouldn't actually hear the sonic boom until the very tail of the Mach cone reaches their ears. However, the pilot, as well as any passengers aboard the aircraft, wouldn't hear the sonic boom at all, because they are travelling faster than the actual sound of the boom. So the sound will never catch up to the aircraft and will never reach their ears. They can sit comfortably in their cabins, sitting lattes whilst travelling faster than the speed of sound in relative silence, unbeknown to the fact that they're deafening every poor sod that they pass below. Contrary to popular belief, a sonic boom doesn't just happen once as an object breaks the sound barrier. The Mach cone and the sound of the sonic boom are present for the entire time that the object is travelling faster than the speed of sound. For as long as the aircraft is travelling at this speed, the boom remains a constant noise that follows the aircraft around. So that explains the sound. But what about the visual effect of a sonic boom? What causes that weird cone-shaped object to appear behind the aircraft when it breaks the sound barrier? This is caused by a rapid change in air pressure, which is caused by the high velocity of the aircraft. This drop in air pressure causes the temperature in the atmosphere behind the aircraft to drop significantly, causing condensation in the air. So what you're actually seeing is water vapour in the air undergoing rapid condensation. But this is not actually directly related to breaking the sound barrier. Condensation clouds from aircraft can be seen at a whole range of velocities. These condensation clouds don't always coincide with a sonic boom. Whether you see this phenomenon or not depends on many factors, such as the humidity of the atmosphere and the air temperature. It's not just high-speed aircraft that can produce sonic booms though. Sonic booms are found in many places in both nature and the man-made world. When you crack a bullwhip, the cracking sound is not caused by the whip hitting itself. The noise you hear is actually a tiny sonic boom, created as the velocity of the whip surpasses the sound barrier. The pistol shrimp is also capable of creating a sonic boom. This tiny little bugger is like the Chuck Norris of the ocean. It can snap its claws together so fast that it creates a sonic boom between its claws. This sound is so loud that it can stun or even kill other sea creatures. That's basically like being able to kill someone by clapping your hands. For goodness sake, nature, calm down. That's just a ridiculous amount of power to give to a shrimp. But it does go to show, anything we can do with technology, nature has probably already beaten us to it. Thanks for the view, subscribe for more, 42.
Alright, so I think that explains well on the sonic boom part. All right, so we'll take a look on one example here, not related to sonic boom though, but it's with the both receiver and the source are moving. Okay, so this says that motorbike or motorcycle and the police car are moving towards one another. The police car emits sound with frequency of 523 and has a speed of 32.2 meters per second. The motorcycle has a speed of 14.8 meters per second. What frequency does the motorcyclist hear? Use the speed of sound as 340 in air. So we have a scenario of both moving. I think we are going to address that here. All right, so we are going to use this equation F O equals to V plus or minus U O and V plus or minus U S. Okay, so speed of the observer and then speed of the source, and F sub S. Okay. So in this case, the motorcycle and the police car are approaching each other. Okay. So in that case, in the numerator here, if you have the observer is approaching the receiver, then you take the plus. Okay, you take the plus there. And the denominator here, if the source is also approaching the observer, you take the minus. Okay, so depends on. So numerator is purely just referring to your observer. If it's approaching, you take plus. If it's away, you take minus. And then denominator is just related to the source. If it's moving towards the observer, you take minus. If it's away from the observer, you take minus, plus. Okay. So in this case, you'll do 340 as the speed of the sound. And because your observer is approaching the source, so you take plus. Okay, plus 14.8. In the new denominator here, you use the 340 again. Now, your source is towards the observer, so you take minus, okay, minus 32.2, okay, and multiply by 523 hertz. So you'll get 603 hertz, okay, for the frequency heard by the motorcyclist. All right. Okay. The next two sections are about the application of sound waves, etc. So the first is the hearing. I think we know that very, very well. So it's basically the sound wave hits your eardrum, and then that's giving signal to your nerve system, etc. Okay? Another application, medical application, will be ultrasound. Okay, so you can see. So this is the ultrasound for baby in the womb, okay? And then you can also use ultrasound to detect tumor in the body, okay? So I think you guys can read through this section easily, okay? All right, and we'll stop here, okay, for today. So just remember to study for the exam. Next week we'll have our exam, okay? All right. Have a great break, guys.